we're going to look at the graphing calculator and trigonometric functions. This is a great tool both for verifying you're doing something right or sometimes just to do it. And so we're going to look at graphing, and let's start with a sine curve. So we'll do sine of x, parentheses. So when I graph that, there's the basic graph. This tells you it's working, and when it's done, oh, it's done working, but it's got some weird things here. That's because there are two things you need to do before you graph trig functions. So what I'm going to do is write down these couple of things. So graphing trig functions on the TI-84 calculator. So the things to remember: 1, you must change the mode to radians, and then 2, make the window reasonable. So let's do those two things. First, hit the mode button, and you see it says degree that's being currently outlined there. So we're going to go down to radians and press enter, and it's now radians. So when I go back here to sine x and graph it, I get what is actually the sine curve. Problem now is that the window is not where we normally look at trig functions. I mean, it's an okay place, it's an okay way, but it's harder to see the things because we're not usually going up to 10 and down to 10 or all the way over to 10. Plus, we're got to figure out, like, where pi is and 90 degrees and all that kind of thing. So, press window. Well, this is like the basic graph, going from -10 to 10 for the x's and -10 to 10 for the y's, and going at a scale of 1. So we have a tick mark at every place that's at every one. Well, instead, let's do a different window. What I'm going to suggest are good windows for doing trig functions is to do -1 for the minimum for the x's and 7 for the maximum. That's because 2 pi is 6.28. 2 times 3.14. 6.28 less than 7, we'll put the integer 7. So most trig functions will go, you'll be able to see what you need to between 0 and 2 pi. And that'll be, so -1 is before 0 and 7 is after 2 pi. And then down here for the y's, we don't need to go up and down as much as that. I think like -3 and +3 is enough. Sometimes we might want to go to 4 on these, or 5, depending upon how much the amplitude is. Now, let's come back up to scale. I would really like it if I could put it in terms of pi. Well, you actually can. Nothing wrong with doing that. If it depends on where you want your tick marks. If you want them in the places like, let's look at, if you want to have 2 pi, and then pi over 2, and 3 pi over 2, which are our main quadrantal angles, and really are most useful for graphing trig functions as well, then let's use pi over 2 as our amount that we want to jump to every time, or our scale. Well, you can put pi over 2 in here. There's a pi symbol there, there as the second function. Put second function, and there's pi, and then divide 2. So that's pi over 2, or the same as 90 degrees. So we can't put degree in here this way, but we can put pi over 2, because that's 3.1415 or whatever. Calculator does it more exact. And then, oh, as soon as I move away, look, it changed it into the decimal number that matches pi over 2. Now, when we do the graph, look at what we can see. A much more focused sine curve, starting there, going up there, and over to there. That's how you do a sine curve. You want to make sure that your mode is in radians and that the window is a more reasonable one. It doesn't have to be this one, but it can be. So remember, the window that I did was x minimum. Let me write these down here. So x scale, y minimum, y maximum, and y scale. So I went from -1 to 7, and this I did as pi over 2, and y minimum, -3 and +3, and a 1 for the y scale. That usually works. Now you can adjust it. When you start doing these more, you can make changes based upon what you see you want for a trig function, especially if they go up and down further, or if the vertical shift moves them way up or down. So right now, let's graph a different one. Let's keep that one there, and let's do one with some changes. For instance, 3 sine, well, let's do one change first. 3 sine x. There. That one has an amplitude change of 3, so let's watch what happens. Ah, look at that. It goes way up and way down, and it's the same curve, it's just been stretched, which is what an amplitude does. Now let's go back, and instead of that, let's change something different. Let's make it the sine of 2x. This is one now that's going to cause a period change. And so if I press the graph, there is the basic function. And now what it's done is it's made the period, when it's 2 pi over 2, the period's now pi. So before the curve went here, now it's going whoosh, whoosh, and then it repeats again. So it does its curving twice in what used to be the distance of 1, or 1 time. Now, if I were to go back to that, and instead of 2x, let's make it 0.5x. That's the same as 1/2. So instead of 2, let's do 1/2 x, and look at what happens to it. Here's the basic sine curve. Now what it does is there's half of it, and now it's going under. So instead of it taking 2 pi to complete its full rotation or full cycle, it's now taking 4 pi. So in 2 pi, it only goes like it did here for the first half. Now it's stretched that way. An interesting way to see it. All right, now let's do it, clear it, and let's do it where it's the sine of, let's say, x minus. Now, you can put a number in, and it'll move it over, in this case, to the right. But let's say I put it in by, say, pi over 2. Okay, or, well, no, if I do 1, I'm going to do pi over 2. I'm going to do pi divided by 2 and close the parentheses there for that one. So now when we graph it, here is the basic sine curve again. And now everything's moved over by the distance of pi. So this moved over pi, this moved over pi. Every point on this first one, they all moved this way. They all moved to the right because it's a, in fact, back to here, because that's minus, it's minus a positive pi over 2. So, and it looks almost the same. It starts making a nice little pattern. Now when we come back here, window. Okay, now let's do the last one of the types of shifts, sine x. And so let's do a minus 1. Okay, yeah, let's do a minus 2. So now when we graph it, here's the basic sine curve. And there it is where everything's been moved down to. If it had been plus 2, this would all move up to. Now we can put all these together. Let's do one final one actually, there where I'll put a few things together. Let's say I do 2. I'll clear that first. So I'll do 2 sine 2 pi, no, 2x, minus, say, pi, parentheses, let's do plus 1. And let's graph it and just see what happens with all those changes. Yeah, it's going, whoa, up and down like that. The vertical shift moved it up. The 2 extended or stretched it that way. the 2 pi compressed it for left, right, it compressed it along the x-axis. And it looks like it also moved by pi, so where it is now, it all should have been back this way by 180 degrees or pi at that much distance. That one's harder to see than the others. But that's why graphing this and getting your negatives, putting everything in the right place, then this can verify that what it's supposed to look like. All right, so once again, enter it here. You make sure that you have a window that's reasonable. You make sure that you're in the right mode of radians, and then you can graph a basic sine curve or all of the changes. And of course, you can do the same thing with cosine. One more thing now, let's look, that sine and cosine are pretty much done the same way here. Let's also look at tangents. I'm going to go back to here, and I'm going to clear these and move that aside. The same basic thing for tangent, cotangent, secant, and cosecant. You still use radians, and you still do this type of window. All right, let's come here and let's look at what a tangent looks like. Tangent of x. And graph it. These are separate ones. And what you can't see is that there is an asymptote that is understood here, because this line goes down and never does it cross over that asymptote either way. So this is a going down to infinity and going up to infinity, and it's almost, by the time it gets way down and way up there, it's almost a straight line. It's never quite, it will get closer and closer and closer to the asymptotes, but never quite touches them. And so this is a set tangent, looks like a million of these going that way and going that way. Now, if I want to do the other three, that's where you have to remember something else. Okay, so you have to remember this, that the secant, let's do secant, cosecant, cotangent. The way you graph those three is using the reciprocal property. The secant is equal to 1 over the cosine. So secant of x is 1 over cosine x. The cosecant is equal to 1 over the sine of x. And the cotangent then, cotangent is 1 over tangent. So let's do, I'm going to do the secant here. First, let's clear that. And since I can't do secant, there are no buttons for that, or no way to put that in there. I'm going to do 1 divided by the cosine of x. And when I graph it, look at what we have. We have parabolas. Well, the reason why those parabolas are there is because the cosine curve is in between. Watch what happens when I put the cosine curve also, cosine of x. The cosine curve, that's the normal cosine curve, and it's at each of the vertices, top and bottom, each relative maximum and relative minimum. And that's the vertex of a parabola. And there's an asymptote in between, just like with the tangent. And those parabolas are what make the secant graph. This and this and this. This is one period of it. This is another period of it. This is another period of it. And you have to sometimes figure out what the asymptotes are, which are then pretty easy because it's the zeros that this crosses over, that the cosine curve crosses over. Now let's do clear both of these. I'm going to put the sine curve back up. There's the basic sine curve. Now, based on the secant and the cosine, you think the cosecant one should be parabolas also that touch here. And it actually is. Let's go and do that. I'm going to do 1 divided by the sine of x. Graph it. And you see we do get parabolas at those relative maximum and relative minimum points. I'm going to keep it going forever and forever. All right. And the last thing to look at would be cotangent. Now, clear that and clear that. The tangent curve remember, looks like this. Starts down here, comes up and goes up. So it's like, starts like in a third quadrant, goes to a first quadrant kind of thinking. Well, if I want to change that, I'm not going to put both up because then you can't tell easily which is which. But I'm going to do 1 divided by tangent of x. And we get the opposite. Instead of going up this way in there, it's coming down, so it's like second to fourth quadrant, like diagonal this way instead of diagonal that way. It's really just like they're flipped in a way. But notice they're not quite flipped. Notice this is the asymptote for the cotangent. The y-axis is here. Whereas when it's the tangent, back to here, and I will put the tangent one on now. Watch what happens with the tangent one. It uses that as midpoints. So the asymptotes for the tangent ones are in between. Hard to see right now, so I'm going to delete that first one so we can see the tangent ones alone. So the asymptotes here for this are pi, or 2 pi, no, that's pi over 2, and 3 pi over 2. Whereas the asymptotes for cotangent are 0 and pi. So inside those rectangles is where they're working. Okay, so now you see how to graph any one of these. And just remember that you want to have your window in the right place. That helps a lot for seeing them. So there's a reminder to make sure that you have the mode in radians. Put a window. This is a good one to work with. You can change it if you need to, especially if you have an amplitude of 4. You're going to want to make it -4 or +4 in order to see it all. And remember the reciprocal properties to help you with graphing the other 3 trig functions. Now you have a better idea of how to graph trig functions on the TI-84 graphing calculator.